This is the Satellite Foundational course for GOES-R on GOES-R aerosol products that are available in AWIPS. Drs. Kondragunta and Huff are major contributors to this task, with additional significant contributions from East van Loslo, also from NOAA SMCD, the Satellite Meteorology and Climatology Division. I'm Scott Lindstrom and I'm navigating your way through this training. What will you take away from this training? Learning objectives are shown on this page. Take a moment to read them. Aerosol products, boxed in yellow, are just part of the constellation of baseline products shown on this page. GOES-R baseline products should be flowing into AWIPS when GOES-R data are flowing. These baseline GOES-R aerosol products are available in AWIPS. Menu items are aerosol detection and aerosol optical depth. The two aerosol products complement each other in some ways. Aerosol detection doesn't tell you anything about the amount of aerosols, for example. It simply tells you that certain types, like dust or smoke, are present. Aerosol optical depth is a measure of the amount of all aerosols, but it says nothing about the type. Why do you need aerosol detection as available in the AWIPS menu? Aerosols affect the amount of radiation that hits the surface, which in turn will affect, for example, high-temperature forecasts. Aerosol detection is important for air quality considerations and air quality forecasts. Numerical models, at least the operational ones at NCEP, do not yet include aerosol loading. There are non-operational models that will predict aerosol motion, and you can find these online. The aerosol products then give you information not routinely available in models available in AWIPS. For the purpose of this training, aerosol detection focuses on dust and smoke and haze. AOD measures the extinction, that is to say attenuation of light, due to scattering and absorption, so it's related to the number of aerosols in the column. As the scattering or absorption increases, because the number of particles in the air increases, AOD will increase. AOD is very low for pristine air with clear skies, but the value can be near 1 if you are in very polluted air. Visibility is definitely linked to AOD and extinction. The inset map shows AOD from MODIS on Terra and Aqua for a day in 2008. AOD can be affected by a variety of events as noted. The aerosol detection product, ADP, is created using reflectance values, so it's a daytime-only product. ADP has 2-kilometer resolution. This is the poorest resolution of the reflectance channels. It's not computed if clouds are present. Aerosol detection occurs every 15 minutes at full disk, conus, and mesoscale domains. Aerosol optical depth is computed every 15 minutes for the full disk and every 5 minutes for the conus domain. AOD is not computed over mesodomains. Land is pretty reflective at some wavelengths, and that reflectance makes it a bit hard to detect aerosols over land relative to water. When and where are these products produced? This slide shows that information for the 3 flex mode domains. Quantitative estimates are limited to solar zenith angles less than 60 degrees, the greenish band in the images of the GOES footprints. A forecaster should be more cautious in using products at high zenith angle. This shows the 2 visible and 4 near-infrared channels on ABI that are used to discern reflectance from the surface and from aerosols. The thin blue line shows transmittance. Small amounts of scattering and absorption occur in bands 2, 3, 5, and 6. That is the red band at 0.64 microns, the veggie band at 0.86 microns, the ice band at 1.6 microns, and the cloud phase band at 2.2 microns. The cirrus band, band 4 at 1.38 microns, is a region of strong absorption by water vapor, and the blue band, 0.47 microns, band 1, is a region of increased scattering. Differences in absorption and scattering by aerosols between all the bands help algorithms identify the presence of aerosol. Reflectance is a function of surface type. This complicates aerosol detection over land. Are reflectance differences being driven by surface type or by aerosols? Aerosol detection over water is more straightforward. Note how reflectance changes as a function of both wavelength and surface type. Aerosols affect reflectance in the atmosphere. The Earth's surface can also be highly reflective. The trick and challenge is to separate the effect of the surface, which is not so interesting, from the effect of the atmosphere, which is much more interesting. The effect of aerosols on reflected visible light varies with wavelength. The multispectral observing abilities of GOES-R, or in polar orbiting satellites, in the visible and the near-infrared are key. Remember that this is daytime only, as noted already, because reflectance is driving the observations of aerosols and aerosol optical depth. All visible and near-infrared bands on GOES-R are used with this product. Some infrared channels are used as well. This slide shows differences in reflectance. Note how the surface features are visible in the 2.1 micron image, but not in the 0.47 micron image. The conclusion is that aerosols will scatter more effectively at the shorter wavelength. Again, multispectral observations are key to determining the effect of aerosols on scattering. The scatter plot shows observations of reflectance from one band versus another. These well-known relationships between the different bands can be used to compute the land surface reflectance first, and then the aerosol signal can be computed. Again, by comparing signals between two different channels and using known relationships about those differences, one of which is shown in the plot. This slide demonstrates how information from different channels can be used to determine the aerosol regime. There are regimes in the plots where clear regions predominate, or thin dust or thick dust. This is the type of information that is coded up in the aerosol detection and AOD algorithms. This shows the same event on top as the previous slide. Very high reflectance with Sunglint swamps any signals from different channels. Aerosol retrievals are not performed where Sunglint is present. For polar orbiter data, this usually shows up as a straight and very noticeable boundary that is parallel to orbit tracks. For geostationary satellites, Sunglint regions move as the sun moves, and the regions are approximately the same from one day to the next. Some of the spectral tests used in the retrievals are shown on this slide. Again, these mostly include looking at a signal in one band and comparing it to a signal in a different band. Aerosol effects differ at different wavelengths. This is the power of multispectral observations. Now let's look at some examples. These true color images are from SUMI NPP for 3 days in late June of 2015. Look at the pall of smoke over the northern plains. Aerosol retrievals detect this feature easily and are shown by the red dots. Your eye should be able to pick out regions of sunglint over the Atlantic Ocean, in the Gulf of Mexico, and near Baja, for example. Here's a true color image from SUMI NPP from a few days later, July 2, 2015. Smoke persists over the northern plains. There are sunglint in this image over the Atlantic Ocean, in the northwest Gulf of Mexico, and west of Baja. Aerosol optical depth is very large in the region where smoke is apparent in the true color imagery. But note that AOD was not computed in regions where the cloud mask misidentified the smoke as thick cloud, over southern Manitoba, for example. GASP is the GOES aerosol smoke product. Note how AOD is computed during the daytime only. You can see the sweep of the terminator in the imagery. This is a product you can look at before GOES-R's launch to familiarize yourself with geostationary observations of aerosol optical depth and aerosol detection. It's available online, and the link is at the end of the training. AOD and aerosol retrievals are a challenge over very reflective surfaces, especially for dust. So you may see cases where there's an obvious dust signal over land in the visible, but little signal in the aerosol products. Dust detection can be hampered if dust is misclassified as a cloud. This very obvious dust event was not detected well by reflectance-driven retrievals, although the brightness temperature difference, 11-12 microns on the sounder, had a modest signal. Why? It's likely that the cloud masking misidentified the region as cloudy. If you see a dust region with no signal, check the cloud mask. This is available in the AWIPS menu under the GOES-R product Clear Sky Mask. Here's another example of dust over a surface with high reflectance, the desert southwest. This is an obvious blowing dust event, but again, if the AOD shows little signal, as in this case, consider the cloud mask as a culprit. The cloud mask is especially culpable if simple tests like the 11-12 microns shows dust. The Terra Aqua modus brightness temperature difference imagery captured this dust event very well. For this event, AOD detection driven by reflectance had some large signals, but not a lot. Dust over the ocean is more easily detected by reflectance-driven retrievals because surface reflectance over the ocean is smaller and less variable. Note the plume of Saharan dust over the southern Gulf of Mexico in this visible imagery. It is suppressed convection. Because this is over the ocean, it should be detected. The VIIRS retrieval of AOD show enhanced values over the southern Gulf. The takeaway is this: dust detection is difficult over land, but not so difficult over water. Smoke detection is relatively easy over both land and water. Some reminders as you use the Aerosol Baseline Day 1 products. There are no useful values where it's cloudy, at night, or over bright surfaces. Very thick smoke can be misidentified as cloud, in which case aerosol products aren't computed. Here's where to find more information if you want it. Click on the links. This concludes the GOES-R baseline training on aerosol products. Thanks for your attention.